All right, let's take a look at lessons 2.3 and 2.4. Today, we're going to be focusing on rewriting exponential functions into equivalent forms, which just means we're going to be transforming exponential expressions. As a reminder, what makes something exponential is when you have some base raised to a power, and that power is where your independent variable would be. So I'll put an x there. That's where your independent power would come. This would be an exponential function. That would be exponential. An exponential function would be any function where you have a base raised to a power, and that power has the variable. We're going to be talking about the different ways you can rewrite those. So some examples today that you're going to see is we will take like something like 5 to the power of x plus 1. And we're going to look and learn how we could rewrite that. In particular, you're going to learn that this could be the same thing as 5 times 5 to the power of x. You're going to see a lot of things like this today. These are equivalent, and that's what we're going to be doing today. It's really applying transformations. Okay, so that's the goal today as we go through. Let me slide that down so you can see better. Is we're going to be looking at a lot of things like that. Before I get going too fast, I want to quickly go through what lesson 2.3 is all the way about, and then we'll spend the rest of the time dealing with lesson 2.4. Okay, so 2.3 is just the basics of exponentials. On this slide here, it goes through the basics. An exponential function has the general form, start there, and I want you to put in a times b to the power of x, where b is your base. Now, in this situation, the initial value is a. Whatever value is right there, that's your initial value. Also, a cannot be equal to 0. And your base needs to be greater than 0. Okay, now this is for exponential functions. A geometric sequence can have a negative base, but exponential functions, the base has to be greater than 0. That's going to be a little bit of a difference. So here are some pictures here. This one is exponential growth. That's when your a is positive and b is greater than 1. You have exponential growth, and they gave you a point there. I'm going to give you more points in a second. There's also exponential decay, and that's when your a is positive and b is between 0 and 1. But those aren't the only two situations. So to show you all 4 possibilities, on the next slide, we're going to fill in a little table. So what we're going to do is we're going to label each one here. If you have a function or an exponential function where a is greater than 0 and b is greater than 1, what you would have is exponential growth. What I want you to do here is we're going to draw and add some points. I want you to put a point here. And let's just draw another point right there that we're going to go through. We're going to label those points differently in a second. But this right here would be growth. I want you to label this as growth. What in the world am I writing? Growth. Let's try that again. There we go. Now there's going to be 3 key features that I'm going to talk about with every exponential function. The first is they'll always have a horizontal asymptote that they approach. So the horizontal asymptote we're looking at here is this on this side of the graph. It approaches the value y equals 0. So add that in there. This is our first of our key features. This function will approach 0 as it goes to the left, meaning I call the horizontal asymptote right there. That's something, a horizontal asymptote is something you're familiar with from previous classes. But using this class, you could say it this way. You could say there's a limit of this graph. Let's just call it f of x. As x goes to the left, as x decreases towards negative infinity, so it decreases without bound, this graph will approach a certain y value. What y value is it heading towards? 0. Now, it won't be the same on the right. Notice this rises to infinity, and that's why we call it growth. Now, the other 2 key features are this. This initial point here is 0, a, 0, a, put that. to that point. The second point and the third key feature, so first key feature, second key feature, third key feature will be the point 1 comma a dot b. So whatever a and b are, if you multiply them, when you go one value unit to the right, that's where you'd get there. So if a is a 5, b is a 2, 5 times 2 is 10, this point would be 1 comma 10. That's how that works. This point would be 0 comma a. Okay, that's growth. Now let's slide over. This square represents when a is positive and b is between 0 and 1. This is your decay from the previous slide. So the previous slide had both of these. This time, what I'm going to do is I'm going to put my point here and my next point here, and we're going to go through. So this is a decay. Again, it has a horizontal asymptote at 0. So go ahead and approach the x-axis. Add in y equals 0. My asymptote. My key features will stay the same the rest of the way. So what's the formula for the y-intercept? You can look over here. 0a. And the next key feature, the last key feature, this would be, oops, not a first. It's 1 comma a dot b. The last thing I'm going to write is this. If you're saying this graph is approaching this horizontal asymptote, you could write that as a limit. Remember, a limit doesn't tell you where the graph is. A limit tells you where it's going. I'll call this one g of x. This one, as we go to the right, that means as x is increasing without bound, we head to 0. So this is function g this time. This one I named f. Okay, now let's mix it up. What if a is negative? Well, if a is negative, what you have is a vertical reflection. So what I want you to do is on this next graph, instead of it growing up and to the right, it's going to decay down and to the right. This one's going to go down this way. I'm going to have the 2 points be here and there. And I want you this time to draw your graph where it decays. That means it decreases as you go down and to the right. This will also be decay. Now, if you're wondering, wait, what scenario is this? This is when a is negative and b is greater than 1. Go ahead and still put the same key features on. Get used to those. So we'll have that y is, it's approaching y equals 0. These key features should not change. This should be 0 comma a. This point right here will be 1 comma a dot b. Okay, tell me about this limit. What's happening as I go to the left? And I'll call this one h of x. As I go to the left, that means x going to negative infinity. Does my y values increase without bound? Does it, meaning rise without bound? Does it fall without bound? Or is it approaching a flat value? Or is it getting flat? It's getting flat. What's it getting flat with? 0. And so that would be a 0 there. There we go. And last one. Any guesses on how it should look? If I have a negative a and a v between 0 and 1.
Reflection on the x-side.
It'll be a reflection of this graph. So coming up, so if you take your points, just reflect it. So this point will be underneath like that. And so have your graph go up this way. Would you call this growth or decay? I hear growth, and I agree. It's growth. By the way, with exponentials, they're either always increasing or always decreasing. They do not change direction. They're doing one or the other. Add those key values again. So we have 0, comma a and 1, comma ab. All right, this time, let's see, I've named one F, G, H. I'm going to call this one K. This time we'll say the limit of K of X equals as X, this time as it increases without bound. What happens to our value as we get further and further to the right? What happens to our Y's? Do they rise? Do they fall? Or do they get flat? They get flat. They are always slightly increasing, but they're approaching the value 0. Okay, so that really is what lesson 2.3 is all about. It's about understanding how A's and B's work together to give you those graphs. So I have, now that's kind of your notes for lesson 2.3. Now I'll have some just quick hits on one slide. I know it's all small, but then we'll move on to 2.4 material. So here we go. For lesson 2.3, it says here, identify if the exponential function is growth or decay and justify your response. On this one, tell me, what is my, here's what I'm going to do. I'm going to ask for the A value and then the B value. What is my A value on this first problem?
2.
So put A equals 2. Now, if you look back on the cheat sheet, you're supposed to determine if A is greater than 0 or less than 0. Is 2 greater than 0 or less than 0? Okay, now tell me about my base.
1 is less than 0.
Okay, so this time put your base a little bit to the right, not quite centered, and I'll show you why. Our base is equal to 0.6. The option was the base is either greater than 1 or is between 0 and 1. Is 0.6 greater than 1 or in between 0 and 1?
0, 1.
Okay, so that's why I said you scoot it over, because we're going to have less than, or 0 is less than B, which is less than 1. Okay, so find the square that has A being greater than 0 and B being between 0 and 1. Which square was that? Top left, top right, bottom left, bottom right. Which one has A being greater than 0, B being between 0 and 1? Top right, it's this one. So what will we call that?
Decay.
Decay. This is decay. This is the justification right there. Okay, let's see if we can go a little bit quicker this time. On the second one, what's my A?
2.
2, which is greater than 0. What about 7/5? This is greater than 1. Good. So when your A is positive and B is greater than 1, what do we have?
Growth.
Growth. It's growth. Example 3. Just tell me if I need me to slow down. What's my A value? 4/3. Is that bigger than 1 or less? Excuse me, bigger than 0 or less than 0? Greater than 0. What about B? Less than 1, but it's positive, so it's in between 0 and 1. A is positive, B is in between 0 and 1. That would become, once again, picture number 2. And what about the fourth? What can you tell me about the A value?
It's less than 1.
It's less than 1, but that's actually not what matters for A. What matters for A is if it's positive or if it's negative.
Positive.
This is positive, so it's greater than 0. My base is 1.3. What can you tell me about that base? It's greater than 1. So this would be growth. This would be picture 1. All right, examine the function f of x equals 3 times 2 to the x. What are we doing to the initial value 3 when the input is x equals 5? Well, what would happen is this. If you plugged in a 5 there, you'd have 3 times 2 to the 5th. Now, can I multiply the 3 and the 2, the a and the b? Can I multiply those right here? What do you think? Can I multiply right here and say that's the same thing as 6 to the power of x? Is that true? No, that's not a true statement. And here's why. Because if you plug in a 5, this would be 3 times 2, and there would be times 2, times 2, times 2, times... There's 5 2's. Is that the same thing as the 6 to the x power? No, this is not 6 times 6 times 6 times 6. It's this. So that's what's happening there with exponential. No, you cannot simplify a and b. So that's the note here. Just note a and b do not simplify together. A and b do not simplify together unless a equals b. That's the one exception. If they're equal to one another, then you can simplify them. But other than that, if they're not equal, you cannot simplify them together. All right, the next one, let's just simplify this. We have 4 times 4 times 4 times 1.5. Which value is a? What do you think is a in this scenario? Okay, what made you say 1.5 is the a?
It's not repeating.
Okay, so that would be the a value. It's 1.5. And the repeating value is your base. My base is 4. And put an x here. You know, you might be saying, why am I putting an x when there's 3 of them? Because this is saying to write the equation. So that's where the equation came from, where x equals, and this is where I want you to put the 3. Okay, last one, we'll close it on lesson 2-3. How would we write this one? Which value is a? 3.2. It's the one that's not repeating. What is my base that repeats? 0.8. For your equation's sake, put an x there. But for this particular example, how many x's did I have? 2. So x equals 2. Okay, now we're going to start lesson 2-4. So I have 5 important, very, very important exponential rules that I have put on your packet here. All right, so we're going to look at the 5 different rules. When you were working in Algebra 1 and Algebra 2, and you came across exponentials, you had some power rules, and you might not remember them unless you see them this way. If you had x to the 5th times x to the 3rd, how could we rewrite that? Well, think about this being x times 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 x. How many x's did I just say there? I think. Yeah, I think it was 8. What did we do? We took, it's the same base, you can combine them together. And so it's 5 plus 3. Now, what is 5 plus 3? You just told me. 8. That would be x to the 8th. And that's the product property. Or here. This is 2 times itself an unknown amount of times 2 times itself 3 times. How could we rewrite that? X plus 3. Whatever unknown amount we have here, just add 3 more 2's to that unknown amount and you'll have your value. So x plus 3. That's the product property. The quotient property is very similar. Think about canceling. What if I wrote out the x's 5 times? X times x times x times x times x. And then divide it by x squared, x times x. You would cross out 2 of those x's, and how many x's would be left over? 3, because 5 minus 2 is 3. That's the quotient property. Or in this case, how could I rewrite this one? 2 cubed divided by 2 to the power of x is the same thing as 2 to the power of 3 minus x. That's the quotient property. Very important property. All right, and now the power property. Whenever you have a base raised to a power, which in turn is raised to a power, you can multiply those powers. So x times 5 to the power of 3. This would be the same thing as x to the fifth times x to the fifth times x to the fifth. Well, how many x's would there be if I rewrote all that out? 15. That's x to the 15th power. Notice you would add those up, but here you could just multiply. Or here, this would be the same thing as 2 to the x times 2 to the x times 2 to the x. Well, that equals 2 to the 3x. This x plus this x plus this x adds up to 3x's. That's the power property. And two more rules we're going to look at. A fraction exponent and a negative exponent. Okay, the fraction exponent. When you have a fraction exponent, the denominator of that fraction is like a root. So a lot of you are familiar with the square root. What that is, it's a fraction power of half. So let's look at some examples. Here, I gave you x to the power of 3/4. That fourth is a dividing power. So a dividing power is the same thing as a root. In this case, a fourth root of x cubed. That's how you would rewrite that. Or in this case here, 4 to the power 1/2. The 2 is doing the dividing. That means it's the root. So it'd be the square root of 4 to the first power. Which we could rewrite that, by the way. If it's a square root, you don't have to put the 2. And if it's a first power, you don't have to put the 1. You could just rewrite it as the square root of 4. Do we know what the square root of 4 is? It's a 2. You would simplify that to become a 2. That's right. And our last one here, a negative exponent. A negative exponent, how you can get rid of that is by taking the reciprocal of the base. So one thing that might be helpful is you could add like a division of 1. So what happens is your base gets flipped. And you know what? This was not good to me. I should have done another example that's a fraction to begin with. Let's do 3/4 to the power of negative x. Go ahead and add that. We're going to have 3 examples here. So what is x to the power of -3 equal to? It's equal to 1 over x cubed. So notice you just flip the base and the power goes down to the denominator. Or here, 2 to the power of -x, that's the same thing as 1/2 to the power of positive x. 1/2 to the power of positive x. Okay, and the last one, 3/4 to the power of -x. This becomes 4/3. And let me put this in parentheses so you can realize the whole thing's being raised to that power. That would become 4/3 to the power of positive x. So each time you just take the reciprocal. Each time you just take the reciprocal. So those are the 5 rules we're going to use today. So what were the 3 properties called? Product, quotient, power. And then we have 2 other rules, which are how do we treat fractions that are exponents and how do we treat negative exponents. All right, with all that, we're going to use all 5 of those rules. What we're going to do, this is now lesson 2-4. If I were smart, I would have changed that to a 2-4. From here on out, we're going to be working like all this. I should be having 2-4 on all of these. This is when lesson 2-4 starts. What we're going to do is we're going to learn this, that a horizontal translation, when it comes to an exponential function, a horizontal translation and vertical dilation could be one and the same. These two could be equal to one another. I know it sounds crazy, but the reason they could be equal, we're going to see using those rules, that a horizontal translation means you're adding or subtracting a number to the x. Horizontal means x, you're adding or subtracting a number to x, is the same thing as a dilation, that's multiplying the y's. So here's a picture for you. You see how this is the graph of 2 to the power of x? This is the graph of 2 to the power of x plus 3. This is the graph of 8 times 2 to the power of x. I want you to compare these two graphs. What do you notice about the red in these two graphs? They're the same. What we're going to learn today is 2 to the power of x plus 3 is equal to 8 times 2 to the power of x. We're going to learn about that today. Here is a horizontal translation. This is a vertical dilation here, the 8th. So we're going to learn how they're equal today using our properties. So let's jump into it and see how these work. Oh, forgot one. We can also use the power property to see that a horizontal dilation is equal to changing a base. A horizontal dilation can be the same thing as changing my base. Horizontal dilation, that means multiplying the x's. It's the same thing as changing the base. So here, 2 to the power of 3x is equal to 8 to the power of x. We're going to learn about that today. So jumping in, let's look at example 1. It says determine the transformations for the following exponential functions. So here I have 4 times x plus 2. On your example 1a, you see how we have 4 to the power of x plus 2? What I'm going to do is walk you through how we can rewrite this. Now first, before I move on, when I add 2 up there, is that a horizontal or vertical transformation? What type of transformation is this right now?
Horizontal.
Horizontal. That means I'm changing the x's. And when you add or subtract, what does that do to the graph? Does it translate it? Does it dilate it? Or does it reflect it? Which of the 3 transformations does it do if you add or subtract a number? Adding or subtraction is always translation. This is a horizontal translation. And which way would it actually move? Is x a truth teller or a liar?
Liar.
So put horizontal translation left 2 units. That means we would actually subtract 2 from all the x's. Now what I'm going to do is show you what this could be equal to using our powers. So I want you to do an equal here. And we had a property. What is the same thing as adding exponents together? Go back and look at your properties. When you're adding exponents, that's the same thing as doing what by property name? So go over here. Which property has adding exponents? The product. When you add exponents, that's the same thing as multiplying common bases together with each individual power. So what I'm going to do here now is we're going to say this is equal to 4 to the power of x times 4 squared. And I'm going to name this by property before we simplify. Which property did we just do there?
Product.
This is the product property. Now here's how I want to get the final answer. We can reduce one of these. Can I reduce 4 to the power of x? No, but I can reduce 4 squared. What is 4 squared? Now this is my initial value. I'm going to put this in the front. I'm going to say this is the same thing as 16 times 4 to the power of x. This 16, the initial value, is the vertical dilation. Dilation means you're multiplying. Whoops, forgot the C. Vertical dilation. I can't spell. Let's try this again. Dilation. There we go. Vertical dilation. And you would say by factor 16 because that's what you multiply by. So for this particular function, I want you to make note of this. Horizontally translating this function left 2 units was the exact same thing as vertically dilating it by a factor of 16. These were one and the same. You see how with exponentials we can change transformations? This horizontal translation became a vertical dilation. So let me ask you this. Does a horizontal translation become a vertical translation?
No.
Very good. I'm going to say it again. Did a horizontal translation become a vertical translation? We didn't change which way we were shifting. But what we are saying is a horizontal translation becomes a vertical dilation. Yep. Vertical dilation. Okay, let's do this again. G of x equals 2 to the power of 3x. What can you tell me is happening in my power right now? Multiplication. I want you to go through and look at the property that has multiplication inside the power. Find your that has a power that's multiplying. Power property. Very good. It's the power property. We'll come back and label transformations in a second. According to the power property, what does it say you can do if you have a power that's multiplying? A power that's multiplying, you could change to become. So you're looking right. Power property. A power that's multiplying, what could you do? You could separate them as a power raised to a power. So what I'm going to do here is I'm going to separate, and I'm going to put 2 cubed and raise that to the power of x. Now I'll go ahead and name this one so we don't forget. What was the name of this property? Power property. Okay, so now let's simplify. What is 2 cubed the same thing as? 2 times 2 times 2. You could rewrite this as 8 to the power of x. Now, what did we have here? Let's see. This time at the very start, this is that 3 is multiplying the x. Does that mean it's going to be a horizontal or is it a vertical transformation when you are multiplying an x?
Horizontal.
Okay, put that's horizontal. And when you're multiplying, does that mean you're actually translating, dilating, or reflecting? Play it again. Multiplication, is that translate, dilate, reflect?
Dilate.
Dilate. Dilate means to multiply. Now with x's, it says to multiply by 3. Do x's lie or tell you the truth?
Lie.
So we're not actually going to multiply by 3. What do we do instead?
Divide.
We divide by 3. So what do you put in the numerator if there's no numerator? 1. This is a horizontal, I said dilate. Horizontal dilation. That's what I meant to put here. Sorry. Horizontal dilation by factor 1/3. Now let's see. How did a horizontal dilation by factor 1/3 turn out? Well, it did not turn out. We don't have any other transformation, but what has happened is we changed the base. What was the base?
1/3, 3.
At the very start, what was the base here?
2.
And now what's my base? 8. We changed the base. So a horizontal dilation is the same thing as changing your base. Now, I'm sure right now this is making absolutely no sense. Unless you know your rules. Then it's like, well, I'm just simplifying using algebra. That's true. That's what we're doing. But what I do need you to see is when you manipulate, that's the name of this lesson. If you look back at the top, if you manipulate exponential functions, if you manipulate them, you can change what type of transformations you're looking at. And that's what we're doing today. All right, let's look at part C here. What's different this time about my power? My power is a fraction or a quotient. So we'll have to go see how is it written. When your power is a fraction, I want you to go find that one. So look at your rules. Look back. What is it? What do we do if your power is a fraction?
Okay.
If your power is a fraction, do I use this fraction rule or do I use the quotient rule? Let's see. Does our problem look like the quotient? Is that how it looked? No, it looked like a fraction exponent rule. What do? We're going to change it to where we're doing a root of the denominator and the base is raised to the numerator. That's what we're going to do here. All right, so let's start with this one. And we're gonna say this is the same thing as square root of 9 to the power of x like this. Now, which rule was that? That was from the fraction exponent rule. Fraction exponent. That's where we got that from. Now this can simplify. When you take a square root, you don't actually have to write that 2 there. You can just rewrite it as 9 to the power of x. What is the square root of 9? 3. So I can rewrite this as 3 to the power of x. So what has changed? I started with 9 to the power of x over 2. I now have 3 to the power of x. What did I change? The base. This is not a transformation. This is a change of base. Changed the base from 9 to 3. That's all that happened here. So let's go back and see where did it come from. Was I transforming the x's or the y's here? What was my transformation at the very start with? X. I was transforming my x. Does that make it horizontal or vertical?
Horizontal.
Horizontal. Okay, if you are dividing by 2, is division a translation, dilation, or reflection? What is division? No, negative is a reflection. Dilation. This is a horizontal dilation by factor. Now, does this lie or tell us the truth? So instead of dividing by 2, what actually happened to the x's? We multiplied by 2. So we'd say horizontal dilation by factor 2. A horizontal dilation becomes a change of base. Okay, and I got one more for this section here. What's happening with my exponent this time? Oh, I hear horizontal translation. Do y'all agree that that's going to be a horizontal translation? Is it going to be horizontal?
Yes.
Why is it horizontal?
Minus.
Change in x. When you subtract the number, is that a translation, dilation, or reflection?
Reflection.
When you subtract a number, it's a translation. Reflection is just a negative, like a negative x would be a reflection. Translation, which way would it go if it was x-axis minus 1? Is it a liar or truth teller?
Liar.
Liar. So we actually add 1. It's going to go right 1. Horizontal translation, right 1 unit. Okay, so now go to your rules. What can we say that when the power is subtracting, what does that equal to? I hear quotient property. Let's go check it out. Quotient property. Does the quotient property have a base with the subtraction power? Yes, you can turn that into the base of the positive over base of the negative, the subtracting. Okay, so we're going to change this problem. Now that we're back, I'm going to change this as 5 to the power of x over 5 to the power of 1. The negative portion goes to the denominator. Now, what was the name of that we just got this from? Which property? Quotient property. Let's add that to the notes. That's the quotient property. And now I'm just going to simplify. This is the same thing as 5 to the power of x divided by 5. And then one more time, I'm actually going to change this. What I'm going to do is you could do it like this and say this is 1/5. Oh, I can't cancel those 5s. Can't do that. But I can say this is 1/5 times 5 to the power of x. I can rewrite it that way. So I can't cancel the 5s because this 5 has a power, but I can rewrite it in this form. Now, this 1/5, is that still a horizontal transformation in this form? Is this horizontal in this form here? Am I changing x's or am I changing y's?
Y,
It's on the outside. I'm now changing y. So I would not call this horizontal. I would now call this
vertical.
vertical. When you multiply, is that a translation, dilation, or reflection? Multiplication and division are dilations. This is a vertical dilation by factor. Is it a liar or true teller? If it's vertical, it's a true teller. So it's by factor 1/5. So one more time, a horizontal translation becomes a vertical dilation, and a horizontal dilation becomes a change of base. That was the same all the way through these. So like A and D, if you notice both A and D, they both are a horizontal translation becoming a vertical dilation. That's both A and D. Horizontal translation becoming a vertical dilation. Both B and C were a horizontal dilation becoming change of base. Horizontal dilation becoming a change of base. All right. This time, I'm kind of going to go backwards. And we're going to look at it this way. It says, let f of x be 3 to the power of x. Let g of x be the transformation of f. For each problem, name the transformation of f. Okay, so right now, what could we state about this transformation here? What's the 9 doing? Okay, I forgot what I was saying. So I'm picking back up. Here. What's the 9 doing right now? Is that a vertical transformation or a horizontal transformation? This 9 here.
Vertical.
That is vertical. How'd you know it's vertical?
So just say the Y.
Okay, now if you're, that's right, it's not with x, it's on the outside. If you're multiplying, does that make it, I'm gonna hear everybody this time. The answer is gonna be either translation, dilation, or reflection. What do you think? 3, 2, 1. Answer is dilation. Whenever you multiply, it's being dilated by factor. Is the 9 a liar or true teller? True teller. There you go. By factor 9. Okay, that's all the problem asks us to do, but just to make sure, I'm going to do a little bit extra because we can do it fast. How you could also do this problem. This is the same thing as 9 is the same thing in terms of 3. 9 is equal to 3 squared. So I'm going to rewrite this as 3 squared times 3 to the power of x. Now, I didn't actually do any crazy math there. I just rewrote 9 as 3 squared. What property could we use if we have the same base multiplying? Product property. According to the product property, this is the same thing as 3 with 2 plus x. Actually, I want to write the x first. It'll make more sense if we do the x first. X plus 2. That's the same thing. That right there is the product property. That's what I did there, is I did the product property. Product property is how I got from one to the other. Now, over here, if I gave you the problem this way, this would not have been a vertical dilation. What type of transformation is that plus 2? Vertical or horizontal? That would now be called a horizontal. Now, and it's translation. Why is it not now a translation as opposed to a dilation? Because adding and subtracting are translations. Translation, and if it's x plus 2, which way do you actually go? Left 2 units. Now, that last part was extra. I just wanted to show you how that worked. All right, let's look at part B. Part B, I could rewrite as this. I'm going to make this 1 multiply with a 3 right there. Multiplying by 1 doesn't change things. I could rewrite this as 1 over 27 times 3 to the power of x. Now, if I wrote it like that, What's the 1 over 27? A vertical or horizontal transformation? It's vertical. It's not with the x, it's vertical. It's multiplying. So does that make it a dilation, a translation, or a reflection? Dilation, vertical dilation. If you didn't have these down before, you probably will by the end of this class. Is this a liar or truth teller? So if it's truth, then it's by factor 1 over 27. Okay, just to do the extra that I did before. 27, if you did not know, 27 is the same thing as 3 to what power? Okay, I could rewrite this as 1 over 3 cubed times, which now I kind of wish I hadn't separated, but I did, so I'm going to go ahead and put it back together. This would be the same thing as 3 to the power of x over 3 cubed. And now what property could I do here? Quotient. The quotient property tells us that if it's the same base being divided, what you can do is combine your bases and you subtract the powers. X minus 3 powers. That would be equal as well. This started as a vertical dilation. Is it still a vertical dilation in this form? No, it has now been, the transformation has become a horizontal or vertical? Horizontal translation. Good, y'all are on it now. Which way would it move? Left or right 3 units? Right 3 units. Feel like we've hammered these in a million times over already? All right. It says each of the following exponential functions on parts 3 here, example 3, has a horizontal translation. For each, write an equivalent representation that has a vertical dilation and no horizontal translation. So this time we're not going to be writing all the extra steps. We're just going to simplify it. So we'll go a little bit faster, but just so you can see it a few more times. 2 to the power of x plus 3. What property could we apply here? Product. Good. A product property says that when you have powers that are adding, you can rewrite that as the same base. Why do they call it product? Same base multiplying. Good. So what is that would be 2 to times 2 to the power of x times 2 to the power of 3. Do y'all know what power 3 is? 2 to the power of 3 is 8. There we go. So I could rewrite this as f of x equals, I'm going to put the 8 in the front as my initial value, my a times 2 to the power of x. There's my equation there. By the way, would this be growth or decay? Let's tie back in lesson 2.3. This is, I know it says 2.3 here, but truthfully, this is now lesson 2.4. Would you call that growth or decay? Growth, because this is positive and that's bigger than 1. Good. All right, G, what's happening this time?
Negative.
By the way, I'll just put product property. Product property. All right, what property is going on this time? Quotient. If it's the quotient property, that tells you one base with a power that's subtracting. You can rewrite as 2 bases that are dividing. 3 to the power of x divided by 3 squared. What is 3 squared? So 3 to the power of x divided by 9. And to finally rewrite this, I'm going to say g of x equals, I'm going to make the a be distinguishable. I'm going to say a is 1/9 times 3 to the power of x. Would that be growth or decay?
Decay.
Gotcha.
Growth.
A, it just matters if it's positive or negative. Is that positive?
Yes.
Positive, bigger than 1, it's growth. That would be growth. All right. Example C here. It says to get rid of the horizontal translation. So what am I getting rid of? Getting rid of the 4 or getting rid of the +2?
+2.
Getting rid of the +2. How could we rewrite that? Product property, which means it will be 4 times 3 to the power of x times 3 squared. That right there was the product property. Whoops, I don't know what I'm writing. Product property is what that was. Now let's simplify. What is 3 squared? And we can reduce that one more time. What is 4 times 9? 36 times 3 to the power of x. That would be my function k of x. 36 times 3 to the power of x. Growth or decay?
Growth.
Growth. All 3 of those were growth. All right. This time, what we're going to do is we're going to play around with change of base. So example 4, and I believe we'll wrap up after this. So let's look at example 4 where it says let f of x be 3 to the power of x, let g of x be the transformation of f. For each problem, name the transformation of f. Okay, so right now, this doesn't look like 3 to the power of x at all. So let's try to get it to become a 3 to the power of x with the transformation. So what could we do to 9?
1 9.
What is 9 in terms of a base of 3?
3.
3 squared. What I'm going to do is rewrite this as 3 squared to the power of x. Now, so far, I haven't done anything crazy. I just changed 9. I changed the base to 3 squared. But this right here is a property. What property is this? When you have a power raised to a power. Power property. With the power property, what does it tell you you can do with the if you have a power raised to another power? You multiply. So I could say this is 3 to the power of 2x. So what type of transformation did we do here? Horizontal or vertical?
Horizontal. Vertical.
Whoa, the 2, is it to the x or the y?
Horizontal.
It's to the x, so it's horizontal. When you multiply, that's what that 2 is doing. It's multiplying. Is that a translation, dilation, or reflection? Dilation. Multiplication and division is dilation by factor. Now, am I actually multiplying by 2 like it says to do? No, it's a liar. So what do you do instead?
-2.
You divide by 2, which means it's going to be 1/2. Okay, now let's try this one. This looks crazy. Doesn't have to be. All right, this one. What is f of x? What I'm going to do here is I'm going to substitute. We know we have something raised to the power of -3, but what is f of x? F of x is
3x.
3 to the power of x. Okay, what can you do if you had 3 to the power of x raised to the power of -3?
X combined.
What property could combine these?
Power.
Power property. A power raised to a power. What do you do with the power raised to a power?
Multiply.
So this would be 3 to the power of,
3x.
now believe it or not, there's actually 2 transformations there. The negative is a horizontal. Would this be a translation? Whoops, horizontal. Horizontal. A negative, does that translate, dilate, or reflect? It's a horizontal reflection. Now, don't forget, if you reflect your x's, you actually cross over the y-axis. Across the y-axis. So horizontal reflection across the y-axis, and now the 3. Uh-oh. The thing went out on me. There goes his back, I think. Let me see. Maybe it's not back. Here we go. Let's try this one more time. There we go. That 3. When I'm multiplying by 3, that would be when you multiply, what's that? Dilation, translation, reflection. Dilation. Dilation by factor. Is it by factor 3 or a liar 1/3? Liar 1/3. All right, I have 2 DOLs for you to practice on. Find which of these 2 are equivalent. So which one's equivalent here? And which one's equivalent here? All right, let's finish up with example 7 here. Finding the values at particular points. I want to make sure you haven't gotten too far that you forgot. What do I do if I just have a value to plug in? What would I do if it says h of 1?
1.
You substitute 1 in. So it'd be 2 times 5 to the 1/2. What's it mean if you have a fraction power? What do you do with the fraction exponent? It becomes a root. And in this case, it becomes a square root. So here, if it's a square root, you don't need to leave the 2 there. You can drop the 2, and you don't need to leave the 1 there. You can drop the 1. Can I simplify 2 times the square root of 5? Do we have a square root of 5?
No.
Nope. So I'm just going to say that's my answer right there. And let's do one more here. H of -2. That would be 6. 6 times 2 to the power of -2 thirds. All right, what can we do with a negative exponent? Do you remember that? You take a reciprocal of the base, so it becomes 6 times the power of 1/2 raised to the 2/3. Now, what do we do with the fraction exponent? We just talked about this. Change it to a root. It becomes a 3rd root of 1/2 squared. 1/2 squared. Now, I'm going to reduce 1/2 squared because that's easy math. What's 1/2 times 1/2?
1.
1/4. Now, I don't know the 3rd root of that. So you could leave it like this, or you could do the numerator. I do know the numerator. This would be 6. What's the 3rd root of 1 is 1. So this will end up being 6 over the 3rd root of 4. You could leave it either way. I'm content with either one, but that would be the answer there.